good morning. Today we are into the third lecture of Systems Engineering Management, and we will go through some of the further details. I am Dr. Deepa Philip from IIT Kanpur. So today's learning objectives, major learning objectives include talking about the three activities of Systems Engineering Management. Throughout this lecture, the SEM, the word whenever you see that, we will be referring to the process called Systems Engineering Management. The three activities are the development phasing, systems engineering process, and lifecycle integration. We have seen this briefly in the previous presentation. So if you remember the quick recap, we drew this development phasing bubble, followed by the systems engineering process bubble, followed by the lifecycle integration bubble, and we said that the systems engineering management is the center portion. This area is what we talk about, or it actually is a conglomeration of all the three things where systems engineering management, SEM, is applied to all the three. Now, in this lecture, we will actually expand the whole system and study what are the major aspects of it, what are the major components of it, and how it proceeds. So, if we expand the diagram, it will look something like this, taken from the DAU Systems Engineering Handbook. The systems engineering process, this red circle, interconnects with the yellow circle, which is a development phasing, which results in what we call as baselines. We will discuss in details system baselines, what it is. Then the systems engineering process and the life cycle integration, when it interconnects, we get what we call as integrated teaming. Similarly, the development phasing and life cycle integration, when they connect, you get the life cycle planning, and all of these things are basically done with the help of the SEM process, systems engineering management process. We will take first study what is development phasing, then from there we will see how the systems engineering process gets applied to the development phasing, and then followed that we will see how the systems engineering process gets applied to the life cycle integration, in which complete product. So, you have a bunch of inputs, and that inputs come to the systems engineering management process, or SEMP, or whatever you want to call it. From there we will see how the output, the system design specifications, how do they come out. This is what we will be studying in today's lecture. So, first let us talk about development phasing. Development phasing is the initial part, the first aspect of the systems engineering. Okay. There are many names and nomenclature associated with this. People discuss this in different aspects. But the primary aim of this step is to control the design process. That is the first part. So, the entire design process, you have to have mechanisms to control. So, control means you should establish benchmarks. So, in one way to do it is, if you want to control something, you need something to compare with. Okay. Or one of the simple principles say, you cannot manage what you cannot measure. So, this is the first aspect of controlling. You are trying to manage things what you are able to measure. So, here in this you establishing aspects for measuring or controlling the design process, and also to which you develop the baselines. The baselines means these are the baselines of the system. These are system baselines. We will see what are baselines and how they are developed later down the road. All these two that together it helps you to do what you call as the coordinate the design efforts. Whether you are designing the complete system, or whether you are designing the subsystem, or whether you are designing even the minute components, this all gets coordinated based on what happens in the development phasing. A development phasing, you can think about it as being subdivided into three parts, or three phases, or three levels. So, whenever you see this word levels, or somebody talks about subphases in systems engineering, both are talking about the same thing. It is a subcomponent of a major step. So, the first part of this is called as a concept study. There are many names, fancy names associated with this term. Some people even call it as a feasibility study, but that is not really the right term that we would like to use. We would like to use it as a concept study. So, here what happens is, we basically trying to decide in this phase, what should be done to a large extent. So, the system concept, like somebody says I want to design an auto aircraft or a fighter jet. So, then is the fighter jet needed? Then what is a fighter jet? What are the capabilities? Some of the basic, in a very broad sense, we talk about the concept of a, will it be a fighter, which will be a bomber, which will be an interceptor, it will be a multi-role aircraft, will it be stealth? So, those kind of basic broad functionalities as part of the concept study. But once you have the concept study done and everybody decides, okay, from there we now want to go into the second phase, which is called as a system level. Then in the system level, what happens is you are describing the performance requirements of the system. What are the aspects that you need to talk about? So, if you take the previous example of an aircraft, then here you will be talking about what will be the, how many hard points for carrying ammunition, okay, power, climb rate. So, you are here, you are specifying the performance requirements of the system. How is the system going to perform in different conditions? That aspect, this is the, from the concept stage you come to the systems level, the translation from once you say agree on the concept, then you say what are the performance requirements of the system. From the system, then we move to what you call as the subcomponent level or what you call as a subsystem level. So, you try to decide here what are the components of the system. You just do not decide the components randomly. You decide the components, what are the components of the system that helps you to realize the performance requirements. So, the major question is how are you going to realize the performance requirements and which components should be used. So, if somebody says I want to hit a target which is hit an enemy aircraft that is 100 kilometers away. So, then you might say okay, I might then use a beyond visual range missile system to accomplish that. So, the hit a target that is far, very far, that you can't see is a performance requirement, and then identifying the subcomponent to realize that is the component level decisions. So, here what happens is what are the performance requirements of the subcomponents, we are specifying that. Once you identify what the subcomponents are, and then what are the performance requirements of these subsystems. Here you also end up doing much more detailed descriptions of characteristics. So, once you decide that okay, I am going to use this specific landing gear for an aircraft, you say that this should carry, let us say 30 tons and it should be able to dampen in like 3 seconds. So, something like this. These aspects then translates to, will use a lightweight material, maybe a duralumin alloy, and then we will be using a manufacturing process called like a machining of a hollow tube or something like this, hollow tubes. So, you specify all these kind of aspects in as part of the subcomponents, because you are also looking at something that are required for the production of the subcomponents. So, all of these things put together, we actually call it as the configuration. People call it in multiple names. This is the, some people call here this as the this part system level, it is sometimes called as the system configurations config. This is called as the subcomponent configurations. All are pretty much the part of the development phasing, where the aim is to control the design process and develop the baselines. So, there are multiple names and other things associated with this, but the general idea of this whole system is that you develop the baseline and which you use to control the design process, and through this you will be able to coordinate the entire design effort. Moving on, this whole thing is accomplished through somewhat 3 parallel studies or 3 documents that gets generated out of as the outcome of the development phasing. When I say somewhat parallel studies, this is of importance because they are not really parallel. They are kind of done sequentially, but sometimes they do overlap. So, if you think about this, or if you want to draw it in a time scale, if you assume that here is your time axis going on, time in the x axis, then somewhere you complete your concept study. You can think about this as your concept study. Everybody agrees on, okay, we need something, we need to. So, let us say let us take an example of an unmanned aerial vehicle, UAV. So, everybody decides, okay, the country needs a UAV. So, now the UAV is to be, we should be using it for, it should be capable of doing surveillance and reconnaissance. It should be able to do have an electro-optical and infrared payload. It should be able to designate targets. This, instead of EOIR, you will see able to see in night. So, these kind of things, the broadly everybody agreed on, okay, this is what the capabilities of the system is. Then once you agree here, here is the first decision point, which this decision point decides, shall we go forward, go further. So, should we go more into this? And if the answer is yes, and we think that there is enough capabilities within the system to do it, then you start the first phase of the development phasing or the systems engineering process associated with development phasing, which to the end will result in what we call as a system definition. This system definition is actually called as the functional baseline. So, you decide, you basically kind of start this process, and somewhere in between you would say, okay, I am freezing the stuff here, no more, and this is another decision point. So, these decision points, these triangles that you see, okay, or what we call these as the decision points, they are typically the technical audits, technical or systems engineering audits. This is where you basically reach a milestone, you decide and define things, okay, we want to go from here. So, the systems definition, the first phase, kind of gives you what you call as the functional baseline of the system. Once you have the functional baseline, in the same time, in somewhere in parallel, you can think about that you will have the second aspect going on. It will be something like this, okay, which will result in what we call as the preliminary design. Or it is technically known as the allocated baselines. So, this also has another, somewhere you will end up freezing the preliminary design, but there is a transition point that you should think about, that from here, when the audit happens and the system definitions gets frozen, then you translate that into the preliminary design. So, these translations, this movement from the translating the requirements from one step to another, this usually what we call is as the design definition. So, you have designed something, from there you are moving to the next phase to develop further design definitions, and throughout the some place you will conduct a audit and other kind of technical audits and other kind of stuff, from where you will actually say, okay, the preliminary design looks feasible, nice, and then from there we start something called as this is not strictly overlapping, this kind of starts from here, and it is kind of an outcome of another design definition audit, another technical audit, which generates what we called as a detailed design. Okay. This detailed design is also what we call as a product baseline. Okay. Product baseline is finally translates to what, or is equivalent to the detailed design. So, and this again translates from the preliminary design. So, if you take this UAV as an example, one of the, there are everybody has decided to go forward, and then the system definition, the basic system definition will come something like this. The system definition of the UAV will be, okay, it should be capable of flying 200 kilometers range, about 10-hour endurance, okay. And this actually comes as preliminary design, not necessarily let me repeat this. The basics, first is that the system definition will be, it should be a long range UAV, people say all weather, and then day, night, long endurance, like this. All these aspects that we just draw here comes as part of the system definition. We are not really come into what we call as specific, very specificalities. In a broad sense, we have come across these are the capabilities of the system. And then from there, once we agree on some of the stuff, sometimes it will shell out into, somebody will say long endurance, somebody will say let us say 10 to 12 hours. Sometimes you might come across these kind of numbers in this process even, or a broad agreement, not a really well defined target, but a broad agreement. Somebody will say long range, let us say 100 to 200 kilometer. Sometimes you will come across these kind of numbers also being as part of this one. But it does not have to be, it can be a broad system specification, what you want to accomplish. From there, once you translate to what you call as a preliminary design, then this is where some of the questions get answered. The questions will be like what type of a platform will be. So, sometimes you will say, okay, you want to fly for a long endurance and a long range. So, then somebody will say, okay, fine, let us do a fixed wing platform. So, then the people will have this design like, okay, here is the fuselage, here are the wings, and here is the tail. So, people will do all sort of designs this way. So, some of those stuff will be the preliminary design aspects of it. Then the range, long endurance, as people said 10 to 12 hours. Okay, then the question will be like, okay, this should be a gasoline propulsion, and then people will say how many gallons of fuel or how many liters of fuel. So, if somebody says, okay, we require 10 to 12 hours, maybe 300 liters of fuel. So, then to this, with the engine weight and other things, translates to what we call as, okay, the total payload or the total all up weight to be close to 500 kg, something like this. Okay. So, this iterative process results in what we call as a preliminary designs, where some more things will get more crystallized. The performance aspects of the system will get designed, get crystallized further, and said day and night capabilities. So, then the part of the day and night and the part of the preliminary design, people will say, okay, day we would probably end up using electro-optical payload, whereas in the night we will use infrared. Somebody might say whether this is cooled or uncooled infrared. So, those kind of questions to a preliminary design. A reasonably good document, which is actually called, okay, this is why we call it as an allocated baselines. We kind of allocate the functions to different aspects of the system. Once it is done, then the detailed design comes into picture. Then somebody would say, you are no longer talking about what is the we are no longer sketching the shape of the just the shape of the wing, but here you are basically bringing the detailed design aspect. So, the aerospace engineer might come up and say, in this aspect will be, this wing will be made of a specific airfoil. Okay. Then somebody will talk about the root code, then somebody will talk about the length, then what type of reinforcement, structural rigidity, all those aspects will come out of as part of this. So, here the detailed aspects of the wing, a subcomponent, actually gets specified out. Someone will say about the engine, okay, it requires 12 hours, so it should be air cooled, liquid cooled, what type of engine, 2 cylinders, 4 cylinder, how many cc, what RPM, what type of propeller, what type of power generation capabilities it should be, what type of alternators will be mated to it. All those aspects actually comes out as the part of the detailed system. In this way, you might even decide what will be the power power system, what will be the communication systems. So, in a UAV, if you think about it, in this the system initial part, you might think about as a UAV as having 5 components. So, the UAV will have a airframe, it will have a propulsion, it will have a communication, it will have a payload, and it will also have a control systems. So, in broadly in the functional baseline, we will talk about the all these things in broader sense. In allocated baselines, we start talking about these ones, and then from there we start specifying much further into detail what are the aspects of the system. And you, as I told you, these rectangles, these technical audit points, not rectangles, these triangles, they are the points at which you translate from this is used for translating definitions to next stage. This audit freezes things or some extent revises things. Once you freeze it, it helps you to move to the next stage of the process. And audits are required and necessary, or what some people call audits as reviews, but we will use the phrase audit because it is a dispassionate, just looking at the document. There is no what you call hard feelings, nothing involved in this. And the aim of this whole process is to ensure that the baselines, whatever baselines, whether you are talking about the functional baseline or you are talking about the allocated baselines or you are talking about the product baselines, any one of the baselines, they should be complete in a sense that once it is done, somebody should be able to pick up the document and design forward what to do, and it should be stable and it should be controllable. The complete, stable and controllable are complete in a sense we are not missed out anything major, stable in a sense that it is you are not changing things left, right and center. Our simple way to think about it is, okay, we all decided that the endurance is 10 to 12 hours and it can be 11 hours, it can be 10 and a half hours, it could be say 11 and a half hours, that is okay, understandable. You are not going to come back tomorrow and say, oh, let us change endurance to 24 hours because that changes the design of the system completely. So, stable in a sense is that within acceptable ranges few tweakings are permitted, but generally agreed upon, generally frozen upon. Controllable in a sense that you know what are the aspects of the system and you know that the capabilities that you have within the system, you can design or you can control the design process. So, here is the design process is controllable, that is what we are worried about. So, the systems engineering process, so SEP, what we talk about, the second bubble is actually a top down approach. Top down approach means it goes in a sequential step by step process, a hierarchical process. So, the top down you can think about it as hierarchical. Okay. You start from the concept phase and then you move one after another from one step to another. It is also comprehensive, in a sense it looks into all aspects of the system. It is not just all aspects, it looks into what we call as the functional aspects, it also look into what we call as the system aspects, it also look into what we call as the subsystem aspects. So, it is a comprehensive system. So, once you are done with this, you can use this process, the documents that comes out of it, to design a system or design and develop a system. Then it is iterative, means it is repetitive is the better way to think about it, or you can think about it as we designed, okay, let us say keep an endurance of 12 hours, everybody told about this, and then at some point of time we are taking the UAV as an example. Then after some point of time we came up with, okay, we also need to integrate synthetic aperture radar as a payload, and then we but this, let us say for the time being the SAR is a heavy payload, assume it that way. then we will say okay fine, then when you have SAR, so this endurance translated to let us say 300 liters of fuel, but because of the heavy weight, high weight of this payload, you can only carry let us say 200 liters of fuel. Okay. So, then this 200 liters of fuel directly translates to a reduced endurance. So, then you might not get the 12-hour endurance, you might be looking at an 8-hour endurance. So, then your endurance aspects get revised at this process. So, during the design phase or when you are developing these documents, these kind of considerations will change. Okay, we might say that 12-hour endurance normally, with SAR it will be an 8-hour endurance. This process is called iterative process, one leading to another. Okay. So, it is you say okay, it goes in a one cycle, then it comes back in another. So, you keep on iterating about it. It is recursive. Recursive and iterative are kind of different, because what happens is recursive is a situation where a decision kind of calls the previous decision, or it kind of goes in a loop of talking about the further details, it kind of drilling down further in this case. So, like an example in this case you would be like you say okay, we want to see the capabilities of day and night in the UAV. So, then the obvious question is what will be the way to see in the day? The question let us say we call it as electro-optical, and the night we call it as infrared. Now, the next question is, do we want to have them independent or do we want to have them together? So, if you say okay, these both have to be together, then we need a dual gimbal, and we continue this process. So, we keep on okay, if you need a dual gimbal, then what are the mounting aspects that are required, where it should be mounted. So, then that results in okay, you might have started with the shape of the UAV fuselage, and you said okay, here is what where we will mount the payload. But then once you decide okay, it's a dual gimbal, you cannot do that, you might want to change the mount somewhere here, something like this. So, you might end up iterating through, not iterating through, you might drill down further, you might recursively go down, and then you will iterate back up to where it goes up. So, this is also done, and it is sequentially applied because lot of the time you make one change in some place. This part is that this is also called as the knockdown effect. When you are doing some change in the system spec somewhere, it will have some effect on further down, which a subcomponent might need to be changed to create that. So, you need to go through this process sequentially to ensure that any change, anything that is decided at this goes down all the way to the subcomponent level, where all the aspects of the system, subcomponent and other aspects are taken down. So, in a way to think about this is, it generates the system product and process descriptions by following this. So, in a broad descriptions of the product and the processes, product means let us talk about this as the system product. We are designing a system, and the processes involved in designing the system, both of the descriptions we will get out of that. And it also provides key informations, major information for the decision makers, like what are the aspects. So, like for example, if somebody says okay, the endurance is important, you can't compromise below 12-hour endurance, then the decision maker says okay, synthetic aperture radar is ruled out, no more needed. So, the decision maker's capability to decide what to do. So, this is like what to do and what not to do. These decisions the decision maker kind of makes based on this systems engineering process documentations that we are able to develop, and it also becomes the input for the next stage of the system product development. So, once you freeze all these things, you have gone through this, you have taken care of all those aspects of the system development, system product development, then the further stages we will use kind of the documents that we generate out of this as the Bible to go forward. So, at the end of the day, it is a problem solving approach. It is a top down, comprehensive, iterative, recursive and sequentially applied problem solving process to realize a system that is well thought through as the capabilities as needed and required. So, in a detail, if you think about it, this is kind of the three major aspects of the system engineering process the requirement analysis being the stage 1, and then the functional analysis and the design synthesis. So, how this whole system works out, we will try to talk about it. So, the inputs comes in, then the systems engineering process. So, you can think about this whole thing as the systems engineering process, and then from there we get what we call as the output, which is the design of a system. So, the first thing is the requirement analysis. We showed in the previous slides how the requirement analysis is be done, which kind of is part of the development phasings, which is the concept studies. Okay. And if you think from there, you kind of get into what you call as the functional analysis and allocation. We will talk about what it is later, but to a large extent the requirements of the system gets translated to what we call as the functional analysis. So, the requirement is it is a long endurance, and the functional analysis is like what is it required to realize the functional, what is it required to realize the long endurance, how much liters of fuel, what type of engine, what type of cooling system, what type of automated control, so that the remote pilot fatigue is not impacted by that. All these kind of things comes out as the functional analysis, and then sometimes during the functional analysis you will come across, okay, it can be done or it cannot be done. So, that feedback goes back into this, then the requirements gets revised, and then appropriate functional analysis is done. So, this is sometimes also called as function analysis and allocation. It is called it's because you are sometimes at the end of the day you are say, okay, this function is being allocated to this subsystem. That also sometimes happens as part of this. So, this loop that you did, this loop is called as the requirement loop. So, all the requirements of the system and the functionalities that we are going to put into the system are synthesized out of this loop. So, once you are done, then from the functional analysis and allocation, you allocated the functions to different stuff, and when you successfully complete this loop, the system has all sort of functional capabilities with it, which will be able to satisfy the requirements, system requirements that came out of the requirement analysis. From the functional requirement, what we get to do is the design synthesis. You try to design stuff, and once you start doing the design synthesis, then you will say, oh, that does not really work, because we do not have the capability to do that which we thought we had. So, let us go back and change it actually. When this change happens, then you have to go back to the requirement loop and you have to iteratively do this. So, this loop is called as the design loop. So, this is why I was telling earlier that this process is sequential and it is top down, it is hierarchical, and it is also recursive. So, you from requirement analysis you went to function analysis, you finished this loop, you think you are really got a level where you are kind of confident with this. Then you went into this design synthesis and you realize something, okay, that is not really feasible. You went back to functional analysis and allocation and modified it, which you found out, okay, that will actually compromise some of the requirement analysis. Then you go back and do this loop process. So, this sequence process, you by doing this up and down, you actually iteratively evolve what the system is. Sometimes in the design synthesis, you might even go back to the requirement analysis directly, which this loop, this big loop, what we call it as the verification loop. So, the verification loop, sometimes when you do the design, is this what the requirement said really, or is it something what else you wanted to do? And at the end of the day, you can sometimes, the problem with this whole system is that you can keep on doing this endlessly. There is no end sometimes to this kind of a process. So, the primary question in this is there need to be some amount of balancing. This balancing happens at each step. The process get balanced out of here. So, how is this balancing done? The balancing is done by answering the fundamental question, how much value is added at each level of development. So, here the fundamental question is by doing this, are we adding any value, or is it just doing things for the sake of doing it? So, the systems engineering process to a large extent, has called as the set of tools. So, this balancing activity is also sometimes called as system analysis and control, SAC. So, this balancing activity asks the fundamental question, how much of value is being added, and if there is no value being added, it is just a futile discussion, ignore it, we do not want to go back or we do not want to do it. But if it is something that is worth doing it, okay, let us repeat doing this. So, this balancing activity is also an integral part of what we call as a systems engineering process. So, this SAC is a set of this is a set of tools and techniques that allows you to balance the entire requirement analysis, functional analysis and allocation and design synthesis in such a way that your system analysis can be done with sufficient details and the whole process is well within the control. So, you put the inputs into the system and you get an output in the form of a system specification, whatever which will satisfy the initial requirements, which was part of the concept studies. So, we talked about system analysis and controls, and I said that earlier said that it is a set of techniques and tools. So, I am repeating the same statement, basically saying that SAC is a set of tools and techniques. And what are those tools and techniques do? These tools and techniques actually do what we call as it track the decisions and requirements. So, at some point of time, if you make a decision and how does that decision impacts the requirements of the system is basically is tracked here. There is a video that I would recommend you guys to see. There is a movie called Pentagon Wars, and this movie actually shows the development of armored troop carrier. And it is an example of how sometimes making decisions on the fly compromise the requirements. I would recommend you guys to watch this. How does the Bradley development process is be? There is a lot of comedy as part of this, but if you see the Bradley assault vehicle development, that is described in this one, kind of gives an idea how sometimes decisions do impact the requirements. So, sometimes you make decisions which will fulfill certain aspects of the requirements of the system. Also, second aspect of this tools and technique, this SAC ensures that you maintain the technical baselines. So, the technical baselines were derived as part of our the requirement facing. From there we came up with, okay, these are the technical capabilities that the system need to have, and from the we ensure through this SAC that these baselines are met to some extent, not to some extent, to the all possible extents. And in this process, if you come across you have to do some interfacing in a sense, here you have the man machine interface, you have a machine interface, you have a system environment interface. So, there are many interfaces as part of this. How do we manage those? If you have an electrical system, how does it actually gets connected? How does it gets connected to a mechanical system? An electric signal, how does it gets translated to a particular movement of the torque arm of the servo motor? All those kind of things actually gets done as part of this. How does the human being who is supposed to operate the system will operate the system? How is the guy who is in charge of producing this system will result in producing the system? All those aspects are part of this managing the interfaces. It also involves managing the risks. As I said earlier, if somebody says, okay, fine, in this Bradley assault vehicle carrier, somebody says, okay, we need to put a big gun. That is one of the decisions that they make. But putting a big gun gives it an appearance of a tank. So, then the enemy is going to hit it with much heavier weaponry, which will create much more, which will be a much risky proposition for the troops that are traveling in the system. So, sometimes what happens is the decisions will create risks. When you see this video, you will understand what I am talking about. But anyway, and the SAC's role is to how to manage. You are looking at mitigating, identifying, and understanding. So, once you know the risk, then you basically decide how to deal with it and how to manage it. In all these process, one major aspect that comes out of it is the cost and the schedule. Are we what about the cost and how long the development process is going to last? Is it within the schedule? So, here is the money plus time. So, schedule in a way is schedule is a sequence of activities with definite start and end times plus resources needed to complete the activity. So, we use schedule in that sense in this discussion of this whole systems engineering, that schedule is a sequence of activities with a definite start and end times along with the resources necessary to complete the activity. So, the cost and the schedule, the money, how much money is required and what is the schedule, the time within which it will be done along with the resources, is it there. That part also is being is the control aspect of system analysis and control. We also keep on tracking the technical baselines. So, maintaining and tracking is different, because sometimes what happens is you might end up doing something which would really result in not being able to achieve the technical baseline. So, you have to have a corrective action to get back to that to achieve the technical baseline. So, you keep on tracking that the technical baselines are fulfilled at all the levels. In a way, we also told about this earlier, that once the question adding value, are we adding any value? Okay. And this question sometimes says, okay, it's no, let us not do it. But the question is the question of adding the value, it is always against the technical baselines. So, you are measuring against the technical baseline to decide is it adding value or not. Then you ensure that the requirements, the things that came in the beginning, you fulfill those requirements. So, the requirements actually came in at the beginning as part of the concept study. Concept study gave us some requirements. Let us call it as the broad requirements. These broad requirements we keep on trying to see whether then you crystallized into what we call as a product and subsystem requirements. So, these requirements we ensure that they are being fulfilled. That is also part of this systems analysis and control aspect. So, the tools and techniques allows you to do all of these aspects. That is what we call as the SAC, or the system analysis and control aspect of it. And in this case, again, as I told you earlier, that you have a requirement facing on which you actually apply system and SEP, systems engineering process in an aim to realize the details, the architecture of the system. And in this, we actually will be discussing 3 architectures that pertaining to us. So, the SEP, if applied properly to the development facing or the requirements of the system, then we will be able to derive what we call as a functional architecture, a physical architecture and a system architecture. So, what is a functional architecture? It is the it basically what it does is it identifies and structures allocated functional and performance requirements. So, the functional and the performance requirements are identified. So, if you think about the UAV that we talked about, somebody said it should be a long endurance, which translates to something called as, let us say, 12 hours of non-stop flight in one full tank, something like this. Okay. So, this will be a performance requirement. So, similarly, the functional requirements and its associated performance requirements will be coming out of this. It should be capable of doing day and night watch or surveillance. That comes in, then you will say it translates to EO plus IR dual payload. So, these are, we can think about it in a broader sense. I am just giving you some examples. So, the functional architecture to some extent gets actually described out of this. Similarly, the physical architecture is the you are basically describing the system or depicting the system in terms of its subsystems and components. Yeah. So, here it is much more detailed. You are not just talking about, so here you will be like a infrared, in this case the IR payload, you will probably will be having something like, here is a uncooled or cooled, what is the optical zoom, is there a digital zoom involved in it, how what is the ambient light, is tracking capable. So, many aspects of this. Okay. The subsystem capabilities and its components are of a system, is both the system and as well as the subsystems are completely specified as part of the physical architecture. In this case also we will talk about the shape, the form, we will also talk about the packaging, and that kind of a systems are part of this. Okay. All these things will come into what you call as a physical architectural system. And then comes the systems architecture. This is little bit more broader because it identifies everything. I would say I use the word overarching world everything because it also involves it includes the enabling products. What are the enabling products? These are the enabling products. They are, first of all, they are necessary to support the system. What are some of the stuff that are necessary to support the system? You would require things in the development, you will need something called in the production, support systems in the production, there is stuff in deployment, there is stuff in during the operation of the system, there is support, maintenance, training, they are all part of this. Then there is disposal, training, and also it involves in verification. So, all these aspects, these are all the enabling aspects of ensuring that the system is doing what it is supposed to do. It is done in both senses, that sometimes you might come across something during the physical architecture which might translate to a system architecture and say, so we would require something extraordinary to realize this. That is fine, as long as you end up meeting all of these things are done. All of this is to ensure that the specifications or the needs or the requirements of the user is met. This is the reason why all of these things are. So, these three documents put together, it ensures that the specifications, needs of the system, what the user has specified or user wanted, is being met out of this. So, that finishes off today's one part of the presentation. We will come back with the next aspects of the systems engineering management process in the next presentation. Thank you.